Okay, before we start, I need to see all your enrolment forms to make sure you've all paid. They're just teasing you. You may have heard comments like reading the rocks and so on, but even before I begin that, I thought I would start by asking you a couple of simple questions. If we look down at our feet here, the reason why we've come up here is because there's nice sand. And if I was to ask you, how did it form? What would you say? How would you say this sand formed here? Now, I don't want any smart answers like the Bayside City Council dumped it here last week. Because they do regenerate, but not at Ricketts Point. They actually do it at Brighton. How many people are from Brighton here? So there you are. Obviously you pay more rates than we do. But yes, well, the point about this is that this is made up primarily of one mineral only. Do you know what it is?
Silica.
Sorry?
Silica?
Silica, yes, yes, and silica is silicon dioxide or quartz. Now, it's a very tough mineral, quartz. It has a hardness, and the scale of hardness goes from 1 or 0 effectively through to 10, and quartz is 7. So it's one of the hardest minerals you're likely to find around. And it's called a detrital mineral. Now, how does that there become rock? This became sand because it was weathered and eroded from pre-existing rock. So how did we get this back, presumably going back to rock like that out there? Any ideas?
Lots of heat.
Lots of heat. We don't need heat. Pressure. Pressure is one very good thing. And in fact, if I had a big machine here that I could squash this really hard, it would actually stick together. And then when I put it in water, it would go again. But the rocks out there aren't going, are they? So something else has happened, and it's not necessarily heat. Heat does help, but it's not heat. How come the rock exists? That stuff out there is what we call a sedimentary rock. Now, I know a lot of you get excited about the fact that there may be volcanic rocks around here. Forget it. All of the rocks here are sedimentary. So they were all made from sediment, from grains of sediment. The name sedis is the Latin, which means to sit. So all these rocks out here were made from particles sitting on the seabed. So how do we get from this to that?
Chemical reaction.
Pardon?
Chemical reaction?
Chemical reaction. Fizzing, you mean, or something like that? It's actually not as complicated as it seems. We've got to glue it together. Let's walk down and have a little look at it. Okay, now for those who want to, it's actually bubbling. So what does that mean? It's reacting. So what bubbles? Air? Yeah, actually this is really bad. I'll tell you what I've really done now. I'm going to have Albo, he's going to come down, no, Chris Bowen, because I'm creating carbon dioxide. And I'm actually now, can you feel it getting warmer? It's actually getting warmer as we stand here because I produce more carbon dioxide by putting hydrochloric acid on the rock. So there is that, see the little bubbles in it? Can you see that? Don't touch it, it's acid. So we have a clue. That's quartz, and quartz does not bubble. So it means the only thing that bubbles around here is in fact a carbonate. So when we put hydrochloric acid on a carbonate, it releases the carbon dioxide from the rock. So what has stuck this rock together is in fact calcium carbonate. So what we've got here is two types of glue. The carbonate and also the dark brown one, which is called goethite. Now it's named after the German philosopher Goethe. It's FeO.OH, so it's iron oxyhydroxide. That's the black stuff, the blacky brown stuff. Now that is a latecomer. That wasn't here initially. That only was formed by groundwater moving through the rock after it had been lifted up out of the seabed. So it's all automatically now we're seeing processes that are going on. The rocks here were deposited in water, marine conditions, and I'll show you how we know that in a few minutes. The next thing is that they were uplifted and groundwater moved through them, and the groundwater carried cement with it. And that's the dark brown stuff here. Okay, now, how do we know it's marine, and how do we know how old it is? Two big questions. Who wants to start the first one? Age.
That kind of looks like a shell. Where is it? I'm talking about these.
Yep.
These little shells.
Age, how do we know how old it is? Everybody says, you know, it's 5.5 million.
Carbon dating.
Yeah. That's okay, but carbon dating, the half-life of radioactive carbon is not very great. You can't go more than around about 30,000 years or so with carbon. What we do find in some places are layers of igneous rock that can be very accurately dated to when they were deposited, like lava flows, and we look at the rocks below them and above them and see what they contain, the fossils they contain. And in many cases these are microfossils, and they are very abundant. They are part of the plankton, and it's those sort of organisms that we find in the rocks here that can be very useful. So if we find, for example, a layer of rock that's a lava flow, and it can be dated with radiometric dating as 5 million years old, and above it are sediments, and another lava layer above that one which is 4 million years old. We know the sediments are between 4 and 5 million years of old. But how do we know it's marine? Now, when we go back, I saw some a bit further over there of the fossils that are the common ones here. There's a thing called Ophiomorpha beaumauricensis. So it's named after this particular place here. And it's a big tube about this diameter, and it's very knobbly. And it was produced by decapods, lobsters that crawled under the water, perhaps as far down as a metre below the water sediment interface. And our local authority, they had a beautiful sign up in black rock saying that these were the roots of Banksia trees. And of course that is complete nonsense, because this is marine and Banksia trees don't normally grow in water in this environment. So we managed to convince them that it wasn't Banksia trees, but in fact it's produced by these little wee crabs. Now, if we were to do something with that, to take a photograph of it, we would have to put a scale in. And the scale is a very useful thing to have, so that later on you know how big it was. The great things that happens with a geologist, you go out and you take a photograph of something and there's no scale there, and you go back and you've taken 1,000 photographs and you want this particular one, there's no scale, so it's useless for you. So you always put down a coin. So if I was to photograph this now, I have a coin there, and that coin is exactly 23.25 millimeters in diameter. So if I take a photograph of that, I know exactly how big that fossil is. Now, this here is a grain size comparator. And you may say, well, why do we need a grain size comparator? We can see the size of the grains with that down there. Could you give me my coin back, please? He's nicked it.
Who's Mr. Orange Jacket?
Thank you. Whoa. Okay. So this here is a grain size comparator, and I'll sort of, can you see it from the back there? So it's got different grains in it, and it tells us when we're out in the field, sometimes you lose track of how big things or how small things really are. So this is quite useful. It's clear plastic, so we can hold it over the rock down here and we can see the actual size of the grains in the rock. So this is a fine sandstone. There are not a lot of fossils other than what we call trace fossils. And that one there, those are trace fossils there, but I suppose the most exciting ones to find are these. Now I'm going to show you this, which is kind of interesting, because see that? And what is it? It's a shark's tooth. But this is the way they have been found around here, because this one has worn out of the rocks and it's been covered in what we call coralline algae. That's why it's pink. Now sometimes they sort of move around in the sand and the sediment, and they clean themselves up. And there's one there. That's the same sort of thing there, but that has been nicely cleaned by sediment moving backwards and forwards over it. Now, these here are from sharks. And years ago, when I first came here as a child, you could walk down the beach and probably find these. relatively easy. The last one I found down the beach here was around about 5 years ago. So they're getting a lot rarer now. Okay, now, sometimes in this particular site here, the seaweed build-up can be 1 metre high. Today it's quite low, but if we were going anywhere else in the country, and I'm serious about that, and I was to walk over to the seaweed, I haven't done this today, and I go down like this here and lift it up, we would find that it would be full of amphipods. Nothing here though, not a thing, it's dead. In most parts of Australia, if you walk around the coast, you'll see a lot of barnacles growing on the rocks. Have a look over there and see how many barnacles you see. They are not there. So we are missing amphipods, and we're missing barnacles. So we would perhaps check further along the beach, and if you go to Black Rock, for example, you can find that there are around about 4 or 5 species of barnacles that are quite well established there. There are some here, and in fact there's a very unusual one found down here called Ibla. Now Ibla is odd because it has a shell made of calcium phosphate, and most animals do not have calcium phosphate shells. They have calcium carbonate. Now this rock is new rock. This rock has only formed maybe a few thousand years ago. So the rock there, that stuff, the darker material here, that's 5.5 million years old. But this stuff here is only a few thousand years old. So what's happening is this is forming maybe even as we speak, but it's not quite the same, because if you look at the fossils in it, it's full of fossils, but they're different to the ones that are accumulating there. So it's not quite the same as that stuff. But why we've stopped here and why we're looking at this is simply because it shows geology in action. Understand that? So this is rock forming now. Echinoderms, they're called heart urchins, so they probably have a lot of appeal because of that, don't they? Don't you think? A heart urchin is a nice thing to have. If I was to give you this heart urchin, it would be obviously a sign of my devotion, wouldn't it? But these are shaped like a heart, and they live beneath the surface, maybe down as far as, say, 40 centimetres below the surface, and they had burrows that went up to the top, and they would crawl around and feed. When they were alive, they were covered in fine spicules, and they looked like it was fur, but it's not. They're called sea hares when they're alive today because they look as if they've got fur. But the spicules are made of calcium carbonate. And it's kind of interesting because they say that, you know, the only thing you should leave behind are your footprints, and the only thing you should take are photographs. But this here, these weather out of the rocks. And the point that is made is that if they weather out, 2 things can happen to them. Either they can be picked up and treasured, or they just grind away and make sediment themselves. And I think in view of the fact that you've all shown such a lot of interest in geology, it'd be quite nice if you wanted one, you could take one of these here as a souvenir of today. All right? No. So I should put them down there.